Question 3 then is about this fictional polymer Sponstrube. And the first thing it asks you to do is to spot the repeat units. And repeat units are quite easy because you just look through the structure and find out where it repeats. So you can start essentially anywhere you like. So I'll choose to start there. And we'll say, okay, that's the beginning of my repeat unit. And then you just scan through until you see the same thing again. So we'll be looking for this oxygen, carbon, carbon, oxygen thing. So we scan through to there, and then we find it starts there. So the end of the repeat should look like that. Important thing to check that you've drawn the brackets in the right places is that when you get to this bond that sticks through the bracket at the right hand end, the atom it leads onto should be the same as the one that starts it off there. So you can tell whether your repeat unit's right if you can read through from the last atom of one should connect up to the first atom of the next one. Okay, so that's your repeat unit, which you could draw out. So this is a polyester, and you remember, like lots of polyesters, it's made from two components, a diol and a dicarboxylic acid. So that's the diol bit, that's the dicarboxylic acid bit. B says, what's a condensation polymer? Condensation polymer means that when a monomer unit is added onto the polymer chain, a small molecule, such as water, is eliminated. Okay, so when a monomer is added to the chain, a small molecule, such as water, is eliminated. That distinguishes it from an addition polymer, which is what you get with alkenes, where when you add the monomer on, nothing else happens, it's just an addition reaction. So polyesters and also polyamides are condensation polymers. Part C is talking about hydrolysis. Again, it's an important issue for condensation polymers that you can reverse the polymerization reaction, break them down by reaction with water, which is what hydrolysis means, and you can catalyze that either with aqueous acid or with aqueous alkali. This one's asking about alkali. So you basically get the monomers, but where you have to be careful is that because it's under alkaline conditions, you won't get the dicarboxylic acid, you'll get the salt of the acid. So always be careful. Are we talking acid hydrolysis, which will give you the dicarboxylic acid, or are we getting alkaline hydrolysis, which will give you the salt? Okay, so here, this part, which is the diol component, just reverts to the diol, so you get ethane 1,2-diol, which is that. And that's not ionized. Remember that alcohols are not acidic. But this bit reverts to the salt of the dicarboxylic acid. So you get 5-membered ring there, and then COO minus Na plus on that side, and COO minus Na plus on that side as well. Again, it's a good idea to write down the sodium ion as well, because if it's looking for the formula of the compound, you need to have both ions present. Then it asks you about disposal of objects made from polymers like that. There are two issues there really that probably should be mentioned. The first is that these things are slow to biodegrade, which means that if you put them into landfill, they stay there for a very long time. So that's the first point to make. Slow to biodegrade, and therefore have a very long lifetime in landfill. Don't just say non-biodegradable full stop. You need to spell it out a bit more and say, well, why do we care? Long lifetime in landfill. Second point is that, like any polymer, if you burn it, it tends to form potentially toxic combustion products. Finally, photodegradation. Again, this is common to all these condensation polymers, that the carbonyl groups that they contain can absorb UV light, and that generates an excited state which is susceptible to degradation reactions. And therefore these polymers tend to degrade in the light. Okay, so UV light absorbed by the carbonyl groups generates an excited state which is susceptible to degradation reactions. And that's it for question 3.